welcome to lecture 31 of this course. So, today we are going to look at decidability properties of regular and context free languages. So, what do we mean by decidability properties? Okay. So, we want to answer questions like whether the following language is decidable or not. Okay. So, for example, consider the language A DFA, which is encodings of strings, encodings of the following nature. So, I have a DFA D and I have a string W, and I want to answer whether so D is a DFA and W belongs to the language of D. Okay. So, what this means is that, this particular notation here, so what this means is that, so this is an encoding of a DFA D and a string W. Okay. So, actually we will be looking at encodings of machines, encodings of automaton, grammar in the next couple of lectures. So, it is very important that you understand what we mean by this. So, remember that what is a DFA? A DFA is nothing but a 5 tuple which consists of a finite set of states, a finite alphabet, a transition function again which is a finite function because it goes from q cross sigma to whatever to q, and it has an accept state and a set of and a start state. Okay. So, therefore, it has a finite description. Okay. So, I can describe a DFA in a finite manner basically by a string which has some finite length, and I can look at an encoding of that string. I can convert that string to a binary string or so on and so forth. And of course, W by itself is a string, so I can treat it. So, basically I can always look at an encoding of a DFA and a string W in whatever suitable format that you want. Okay. So, if you want the alphabet to be whatever, things like open bracket, close bracket, symbols of the alphabet, okay, symbols, numeric symbols and so on, things like that, that will help us encode. In a similar manner, we can also encode things like push down automaton. Again, in the case of push down automaton, although we can have a unbounded stack, but recall that the transition function is a finite function. Same thing for Turing machines also. So, Turing machine, the transition function is always a finite function. Okay. So, therefore, always when we talk about encodings, encodings are finite objects. So, now suppose we are given an encoding of a DFA and a string W. Can we check if the following is, can we check whether the following language is decidable or not? Given D and W, whether W is in the language of D or not, or whether D accepts W or not. Okay. Can we write an algorithm to do this? Okay. So, the answer is, so the question is a DFA decidable? So, the answer is yes, it is decidable. So, consider the following algorithm. So, we have input some DW. So, an algorithm is just another way of writing a Turing machine, because if I can design an algorithm, I can always translate an algorithm to a Turing machine. Okay. So, I will be using the term constructing a Turing machine and constructing an algorithm or designing an algorithm in a synonymous manner. Okay. So, we are given DW. So, what we do basically in this thing is that we simulate D on W if D accepts, then accept, else reject. Okay. So, of course, it must always be the case that either D accepts or D rejects, because once you pass through the string, you just have to pass through the string. So, think of D as a graph. So, whenever you read one symbol of W, you take one step in D, and in some finite number of steps you will reach the last state. So, if the last state is an accept state, you accept, otherwise reject. Okay. So, this shows that A DFA is decidable. Okay. So, we want to study these kind of properties of regular and context free languages. Okay. So, now let me just change the context a little bit. So, instead of a DFA, if we were given an NFA, okay, so suppose if we are given an NFA and a string W, can we still do the same thing? Can we still check, can we still decide whether W belongs to the language of the NFA? Okay. So, once again the answer is yes, and here we will use the equivalence of DFA and NFA. So, what we will do is that first we will convert the NFA to a DFA, and then we check, do the same thing. So, we have an extra step at the beginning. Similarly, instead of a DFA or a NFA, if we were given a regular expression and a string W, again we can do the same thing, because I can convert the regular expression to an NFA first, okay. Then I will convert the NFA to a DFA, and then I will check whether W belongs to the language of the DFA. So, all these things can actually be decided. Now, let us look at another problem. Okay. So, let me just make a remark here. Similarly, A NFA or A RE are also decidable. Okay. So, A NFA and A RE are, as I just mentioned. Now, let us look at the second problem, that is empty DFA, EDFA. Okay. So, here in the encoding we are only given a DFAD, no string, and what we have to check is whether so D is a DFA and L of D is let us say empty, is the empty set. How can we check? Okay. So, when is the language of a DFA an empty set? So, the language of a DFA is an empty set if there is no path in the DFA from the start state to an accept state. Okay. So, what we do is we check if there is a path in the DFA from the start state to an accept state using any graph traversal algorithm using, let us say, BFS. If no path exists, then accept, else reject. Okay. So, if there is no path, okay, I will just call this the second step. So, if there is no path, then it means that you cannot reach from the start state to the accept state on any string, which means that the language is empty, which means that we should accept. But if there is some path, then there is some string on which the DFA accepts, in which case we D does not belong to this language, the encoding of D does not belong to this language, hence we reject. Okay. So, once again similarly emptiness of an NFA or emptiness of a regular expression can also be checked. So, I can convert both of them to a DFA first. Okay. So, this is also decidable. So, let me remark here. Okay. Now, let us look at the next language, EQDFA. So, in EQDFA we are given actually encodings of two DFAs and we need to check whether their languages are equal or not. So, we are given a DFA D1 and D2 encoded, and so D1 and D2 are DFA, and L of D1 is equal to L of D2. So, how can we check this? So, instead of designing an algorithm, we will actually use closure properties to prove this, closure properties, and we will kind of reduce this to one of our earlier problems. So, observe the following. Okay. So, L of D1 is equal to L of D2 if and only if, okay, I can write it as follows, that L of D1 minus L of D2 union with L of D2 minus L of D1 is equal to the empty set. Okay. So, if I think of them as sets, so let us actually draw the diagram. So, suppose this is my L of D1 and this is L of D2. Okay. So, let me just for the sake of convenience, let us just denote this as L1 and this as L2. Okay. So, if I denote this as L1 and L2, I can just write this as little simpler way, L1 minus L2 union with L2 minus L1 is empty. So, L1 minus L2 is nothing but this region and L2 minus L1 is nothing but this region. Okay. So, observe that L1 is equal to L2. Okay. So, in this case this is my L1 and this is L2. So, L1 is equal to L2 if and only if this shaded region is empty. Okay. If the shaded region is not empty, then there is some string which belongs to one of the two languages, but not the other. Only if the shaded region is totally empty, then we can say that these two languages are equal. And how can I check this? We have seen that regular languages are closed under set difference and union operation, okay, which therefore implies that there exists a so regular language L such that L is equal to L1 minus L2 union with L2 minus L1, which is the empty set. Now, because there exists a language L, I can construct the DFA for L. Okay. So, starting with the DFA for L1 and L2. So, first what I do is that I construct the DFA for L1 minus L2, then I construct a DFA for L2 minus L1, then I construct a DFA for the union of these two things, and that will give me a DFA for L. And now, using the emptiness of the DFA algorithm, I just check whether the language of whether the language L is empty or not, okay, which means that there exists a DFA D such that L equals L of T. Now, check if this D belongs to E DFA. Okay, if it belongs, then we accept, otherwise reject. Okay. So, this proves that EQ DFA is also decidable. Okay. So, these were three decidability properties of regular languages. So, now let us look at the corresponding properties of context free languages. Okay. So, now instead of A DFA, let us say we have A CFG, and instead of DFA D, we have a grammar G. Okay. So, G is a context free grammar, and W belongs to L of G. Okay. So, how can we check whether the string, whether some string belongs to the language of a grammar or not? Okay. So, to check this, what we first do is that we convert G to a grammar in Chomsky normal form. Okay. Now, once we have a grammar in a Chomsky normal form, okay, Chomsky normal form, say G prime. Okay. So, once we have a grammar in a Chomsky normal form, what we can say is that if we are given a string W, then if W is not the empty string, then every derivation of W will have twice the length of W minus 1 length. Okay. So, what I mean to say is that, so if W, for example, is the empty string, if W is epsilon, then there exists a derivation of W in with respect to G prime having only one step, else if W is not the empty string, then there exists a derivation of W with respect to G prime having twice mod W minus 1 steps. Okay. So, this is what we will use. So, if G prime is a grammar in Chomsky normal form, then there is a derivation of the string W, okay, that has this many number of steps if W is not empty, and if it is empty then there is only one step. So, from the start variable you just go to epsilon, that is all, otherwise there are this many. So, now what we do is that, so our algorithm, so let me continue the algorithm. So, first we convert G to a grammar in Chomsky normal form, then list all derivations of length twice W minus 1 if W is generated by one such derivation, then accept, else reject. Okay. So, you just use this property of Chomsky normal form grammar and we list out all possible derivations that can be generated, and if W is generated then we accept, otherwise we reject. Okay. So, now let us look at this problem. So, this proves that a CFG is decidable. Okay. So, once again a PDA is also decidable because I can convert a PDA to a context free grammar, and then I will convert the context free grammar to a grammar in Chomsky normal form. Okay. So, now consider ECFG how can we check whether the language of a context free grammar is empty or not. So, here the idea is once again to kind of work backward. Okay. So, what we do is that we will mark variables in an iterative manner. Okay. So, first of all we pick a rule, okay, and we look at the right hand side of the rule. Okay. If the right hand side consists only of terminals, we mark the variable on the left hand side. Okay. We do this for all rules. Now, again in the second step, I again pick the rules one by one and I look at the right hand side. So, if there is a terminal or variable that is already marked, then I will if all the terminals and variables are marked, then I will mark the variable on the left hand side, and I keep on doing this until no new variables can be marked. Okay. So, now if the start variable gets marked, then I say that the grammar generates a string, which means that it is not empty, the language of the grammar, otherwise it is empty. Okay. So, the algorithm is as follows. So, first mark all terminals. Next what you do is repeat the following until no new variables can be marked. So, what do you do? So, for a rule, let us say that A going to A1, A2 through AK mark A if A1, A2 up to AK are marked. Okay. So, I will mark A if all of them are marked, otherwise I do not mark, and I keep on doing this process. So, finally, if S is not marked, then accept, else reject. Okay. So, S is the start variable. So, if the start variable is not marked, which means that you cannot generate a string of terminals from the start variable, which means that the language is empty, then you accept, otherwise you reject. Okay. So, this proves that this language is decidable. Now, we come to the last thing. Okay. So, we have EQCFG, where we are given two grammars G1 and G2, and G1 and G2 are CFG such that L of G1 is equal to L of G2. Okay. So, this language is actually not decidable. Okay. So, observe that we cannot use closure properties in the case of context free grammars, because as we had seen earlier, context free languages are not known to be closed under the set difference operation. Okay. So, like regular languages, we cannot use that property, and it turns out that we cannot use any other approach also. So, this is something which is not decidable, although we will not be able to prove this in this course. I mean, we will not be giving a proof of this, but this is something that you should remember. Okay. So, an interesting question that one can ask is well, it is not decidable is fine, but is EQCFG Turing recognizable? Okay. Or if this is not true, is the complement of EQCFG Turing recognizable? Okay. So, of course, both of these cannot be true, because if both of them are true, then it would imply that EQCFG is decidable, which is not true. So, is one of the two statements true? So, this is again something that you can think about. Okay. So, I will stop here. Thank you.